Good morning. So subject code is CEC358 Underwater Imaging Systems and Image Processing. So in this under Unit 2 it is about optical image processing. So these are all the topics under Unit 2, and in this particular video we are going to see about image formation, digitization, sampling and quantization, geometric transformation and interpolation. We will see one by one. So first let us start with image formation, digitization and sampling and quantization. So are all interrelated to each other. So first, how we are getting an image, that is image sensing and acquisition process. So through this process only we can get a digitized image. So images are generated by the combination of an illumination source and the reflection or absorption of energy from that source. So the source may be light, that is the thing where we get the light energy, that is the illumination source. Next, the light is phased on an object, illuminated on an object, and the object reflects some of the energy back and it absorbs some of the energy from the source. So that creates an image actually. Depending on the source, the illumination energy is reflected from or transmitted through the objects. Example, light reflected from a planar surface. So also we can consider patients are taking X-rays. So okay, that also is an example for creating an image. So there are three principal sensor arrangements which are used to transform the illumination energy into digital images. So these are the three principal sensors. So first one is single imaging sensor, number 2 line sensor, and number 3 is array sensor. The incoming energy is transformed into a voltage by the combination of electrical power and sensor material that is responsive to the particular type of energy being detected. Next, finally, the output voltage waveform is the response of the sensor, and the digital quantity is obtained from each sensor by digitizing its response. So these are the two processes. First, what is a sensor? How the image is acquired through a single sensor, that we will see now. So this is the figure. It shows the components. What are all the components present in a image sensor, single sensor. So mostly familiar sensor of this type is the photodiode that we usually know. So to generate a 2D image using a single sensor, that has to be with the relative displacements in both the x and the y directions. So light is energy, light energy, it is given to the diode. So from this the output voltage, we are getting the output voltage. So according to the image intensity, we are getting the output voltage. Next, we are going to see how through a film negative is mounted onto a drum whose mechanical rotation, the drum has to be rotated, which provides displacement in one direction. The single sensor is mounted on a lead screw as shown in the figure. So this figure, it contains one lead screw. So that screw provides motion in the perpendicular direction. So one is the displacement in one dimension, and another one, it provides motion in the perpendicular direction. Okay, one is the linear motion, another one is the perpendicular motion. Because of mechanical motion that can be controlled with high precision, this method is inexpensive way to obtain the high resolution images. So with the least cost, we can get a good quality images through this single sensor. Next, general image formation model. So that is our first topic now. So how the image is acquired, through how sensors are working, and next the model, actual model, what it contains. For example, you contains a scene element. This is the object under source. So here it is the illumination energy from the source. So from the source, the light is falling on the object. So the object, it is given to the imaging system. So next we are projecting the object, and this is the digitized image. So first one is the analog image, another one is the digitized image, that is image plane. Okay. So it contains, we are consider usually images are the two-dimensional function. Okay, two parameters, x-axis and y-axis. So it projects the location. So it is a two-dimensional function. Image can be represented as a two-dimensional function, and usually it is used by the letter f of x comma y. The value or the amplitude of f at spatial coordinates, the value, it contains some value, no, that we called as a intensity. So when an image is generated from a physical process, its intensity values are proportional to the energy radiated by a physical source. So what is actually the intensity? It is the energy radiated by a physical source. So some source will be there that is providing the light. The light is falling on the object, and that radiation is actually called as the intensity. As a consequence, f of x comma y must be non-zero. So intensity should hold some value. It should not be 0. So it should be non-zero, and it is finite. So we are defining the range between 0 to infinity. So next we will start with the process of sampling and quantization. How we are digitizing the image. So in sampling and quantization, so you see the figure, we have two images. One represents the continuous image and the second box represents the digital image. So here in continuous image, it is continuously flowing. That is, it is our eye, the image formed in our eye, we can call it as a continuous image. So actually for processing so many applications, we need to have a digital image to have more accuracy and precision. We are digitizing the image. Now how this process is going through? Actually we have so many ways to acquire the images, but our objective in this particular topic, we should have a digital image. So that is from the sensor, it is a voltage continuously running, so it is a continuous image, but we have to digital that image. The output of most sensors is a continuous voltage waveform, that we know, whose amplitude and spatial behavior are related to the physical phenomenon being sensed. To create a digital image, we need to convert the continuous sensed data into a digital form. So to convert this continuous sensed data, sensor data, we need to have two processes. First one is sampling, another one is the quantization. So what is sampling? So we know it is discretizing the time axis, that we call as sampling usually. So okay. So here you see the image. First this horizontal line A comma B represents, we are taking that to be an axis. So here we are having one waveform. So the same point A and B. So what is this waveform actually represents? That is the gray level transitions. What is the value of gray level here? So usually dark black are said to be here white, the point A at white, it should be, it is mentioned as the maximum intensity, and black color is represent to be the minimum intensity, that is 0. So here at point A, if you notice, it is having the white color, so it is showing the maximum peak. But as the line goes on, so what happens? So we are getting some black color, so we are getting down, and again in the middle there is a gray level transition, so again the peak goes up, and again there is a transition towards black, so the peak goes down, and again at the point B, if you notice, we have a white color, so again the line goes up. So at point B we have a maximum intensity of white, so it is representing with the peak value. Similarly, in sampling, if you take this waveform, so first process how the sampling is going on, we have to mark a line, and from that line we have to get the intensity values, project the intensity values in a waveform, and we have to take that intensity scale, and in the time axis we have to cut the intensity values. So in discretizing with respect to x axis, with respect to time axis, is known as sampling, and we are approximating the amplitude values to the nearest levels of gray levels. So in quantization process, if you notice, so here we are having different quantizing levels. So starting from the white color to the black color, so different gray shades we are having. So and we are mapping each intensity to its nearest quantizing level. So this round off process of intensity values is known as quantization, and discretizing the intensity values with respect to time axis is known as sampling. So after that we are getting only the points in a digital scan line. So the first image represents the continuous image, and the last image it represents your digital image. Let us see for the next example. Okay. In this figure we want to have an image that is need to convert it to digital form. So the image may be continuous, that we know, that is with respect to x and y coordinates, also in amplitude, everything it is continuous. Next, to convert it into digital form, we have to sample the function in both the coordinates, and also we have to sample in amplitude. So digitizing the coordinate values is called sampling, and digitizing the amplitude values is called quantization. So that is the summary behind this. So the one dimensional function in figure, you look at this figure, it is a plot of amplitude, that is the intensity values. So along the line AB, the random variations are due to the image noise. So here the graph is not smooth, it is somewhat scribbling. So why it is? Due to the image noise. Next, the sample points are indicated. Now we are going to see about the quantization. So actually what the quantization? It is indicated by the vertical tip marks at the bottom of the figure. You see here. So there is a vertical marks. The samples are shown as a small white square superimposed on the function. The set of these discrete locations gives the sampled function. To form a digital function, the intensity values must be converted to the discrete quantities. The right side of the figure, if you see, the intensity scale is divided into 8 discrete intervals, which is ranging from black color to the white color. So that 8 levels, we are mapping our intensity to its nearest quantizing level. So that is the process of quantization. So the continuous intensity levels are quantized by assigning one of the 8 values to each sample. So here this sample is assigned to the white color. For example, if you take the points at A, so we are having 4 points. So this actually is mapped to the white color. Okay, that is the highest scale. Next, the assignment is made depending on the vertical proximity of a sample to its vertical tick mark. So that is the proximity, which is the nearest to that 8 levels. The digital samples resulting from both sampling and quantization that we are marking in this figure. So, okay, the first figure we know it is a continuous image. It is projected onto the plane of a array sensor. What is this second figure? It shows the image after sampling and quantization. So far we have discussed about what is sampling and what is quantization. So after these two processes, the image becomes like this. So the quality of the digital image is determined by the large degree by the number of samples and the discrete intensity levels used in sampling and quantization. So that here if you see itself, both the images are not same. Why it is so? Because the levels used in sampling and the levels used in quantization. So if we have more number of levels, then we have more accurate image. That is, the digital image will be more close to the continuous image. So that's the process of sampling and quantization. Next we will see how to represent the digital image. So let f of s comma t represents a continuous image function. So far we have discussed that sensor image. So image we capture from the sensor, the output of the sensor, it is a continuous image. It is of two continuous variables. Let us consider it is having two variables, small s and t. So now we have to convert this function into a digital image by the process of sampling and quantization. Suppose that we sample the continuous image into a 2D array. For example, take x comma y. It contains m rows and n columns, where x comma y are considered to be the discrete coordinates. For example, let us take x is equal to 0, 1 up to m minus 1. So that represents your rows. Capital M represents rows. So this x value, it ranges from 0. Since it starts from 0, it ends with m minus 1. Similarly, the y coordinate represents the columns. So it starts from 0, so it ends with n minus 1. For example, if you take the value of the digital image at the origin, f of 0 comma 0, the next coordinate, how it will be? 0 comma 1. What it represents? It represents the next value in the first row itself. In general, the value of the image at any coordinates x comma y is denoted by f of x comma y, where x and y are said to be the integers, that is the locations or the coordinate system. The section of the real plane spanned by the coordinates of an image is called the spatial domain, with x and y being referred to as the spatial variables or spatial coordinates. So how to plot this digital image? So let us consider the coordinates. We know x-axis, that is the y-axis, that is the origin 0, 0, and the next point is 0, 1, like that it is go, and this last value represents the x-axis, the last value represents m minus 1. Similarly, in the y-axis, the last value represents the n minus 1. So these dots represents the pixel, that is picture element, it is called as a pixel. So a digital image is composed of m rows and n columns of pixels, each dots representing a pixel, each storing a value. So the first line is 0, 0. So this is rows. So okay, x-axis represents rows and this y-axis represents the columns. So the pixel values are most often gray levels and it ranges from 0 to 255. What is this intensity values? It is any one of the value between 0 to 255. Okay. So 0 represents black color and 255 represents the maximum white color. For example, if you take this digital image, so this letter capital D image is plotted as a surface. So we have two coordinates, one is x and another one is y, and the toply we have f of x comma y, which represents the intensity value. So here if you see the image on the right side, so here we have 0 represents three intensities we have. So one is 0, another one is white. So here in somewhere middle we have white, and in somewhere we have the intensity to be the 0.5. What it means actually? 0 represents the minimum value black color, 1 represents the maximum white color, and the gray shades. So in this image we have three colors now. So one is a black color, one is a white color, another one is a gray color. So the gray colors are represented by the intensity 0.5, the black is represented by the value 0, and the white lines. So here if you see the image we have white lines, so it is represented by the intensity 1, the value 1. So it is like this the image is represented. So in this figure also you see we have two axes, one represents the spatial location and the third one represents the intensity values. So this representation is useful when we are working with the grayscale sets, so whose values or elements are represented by triplets. So that is x comma y comma z, where x and y are represented to be the spatial coordinates and z is said to be the value of f at that location. So where f represents the value at that particular location. So next it shows capital F of x comma y, it would appear on a monitor or photograph. So how it is appear on a photograph? Here the intensity of each point is proportional to the value of L at that point. In this figure if you note there are three equally spaced intensity values. So if the intensity are normalized to the interval 0 to 1, then each point in the image has the value of between 0 to 1, that is 0, 0.5 or 1. So only we have three colors. If you see here we have only three colors. So the one is black color, the outer border you see it has black color. So next inside that letter D is represented by white color, and in between we have the other color, that is 0.5. So a monitor or a printer simply converts these three values to black, gray or white respectively. So this representation is usually to display the numerical values as an array. So we are usually representing this as an array. So that is location. In this example we have f is of size 600 cross 600, and so how many elements we have? If we have 6 into 6, 6 are 36. So 36 3,60,000 numbers. So that much pixels we will be having. So when developing algorithms, this representation is quite useful when only parts of the image are printed and analyzed as numerical values. So that we are going to represent in a digital image. Also we can represent the digital image in the form of array. So for example, f of x comma y is equal to, so we can represent the location in the form of a matrix. So the first point represents the origin. So if it is f of 0 comma 0, it means the intensity value at the origin has to be noted in this array. Similarly, no, this is the column n minus 1, that much columns, and here if you see m minus 1, it represents the rays. So each element of this matrix is called the image element, that is picture element. We can also call it as a pixel, or it is called as a simply pill. Sometimes it is advantageous to use more traditional matrix notation to denote a digital image and its elements. So since it is very tough to represent f of 0 comma 0, so with the brackets and all, so simply we can easily note it as a of 0 0, a of 0 1, like that we can able to represent. So next we will see the quality of the digital image. After converting the image to digital, we have to check whether it is of good quality or not. So for that we are going to speak about spatial and gray level resolution. So it is a measure of the smallest discernible detail in an image. So spatial resolution, how we can define this? One is line pair per unit distance or dots per unit distance. What is this dots per? Simply we are calling as DPI. In generally, while using the mobile phones with the images while we sharing, we are used to tell how much DPI it will be. Like that will be while zooming everything, we can able to note the difference. So what is the DPI? DPI is nothing but dots per unit distance. It is a measure of image resolution used commonly in the printing and publishing industry, expressed as dots per inch, that is DPI. For example, if you see, newspapers are printed with a resolution of 75 dpi, magazines at 133 dpi. So like this, so many examples we can define. So for example, if you see the figure, actually what it have be, so if we have more dpi, the figure looks very good. So that is, first figure represents 1250 dpi. So slowly if you see, the last figure is 722 dpi. So that much the quality of the sampling process. So this is also spatial resolution. So here the first you see the pixels. So this is the pixel size. So how much pixels if you are reducing, how much it will be, the figure will looks like. So it will be very clear or not clear. Similarly, this also spatial resolution. So it seems like squares. So in the last figure, if you see, it is 32 cross 32. It seems the figure seems to have more squares. But in the figure first one, if you see 1024 into 1024, that much amount of pixels you are using. So that is that much dots you are using, so it looks very good. So the quality depends amount of pixels you are used to represent an image, that represents that gives the good quality. If you reduce the amount of pixels in a image, then it gives low quality. So next we'll see, first we'll see about spatial resolution. Now we'll see about intensity resolution. It refers to the smallest discernible change in the intensity level. So the number of intensity levels usually is an integer power of 2. The most common number is 8 bits, with 16 bits being used in some applications. So this intensity quantization using 32 bits is usually rare. For example, it is common to say that an image whose intensity is quantized into 256 levels has 8 bits of intensity resolution. So you see the table here. So what is the final motive? We are going to represent that to be transmitted, this number of bits is more matters. How many number of bits are used for a particular intensity level? So that is already we said about, it is in the power of 2. So first is, for example, if it is 2 means the number of bits will be 1, that is either 0, only we have 2 levels to represent, means only we have 2, that is number of bits is 1. So if we have 4 intensity levels, that is 2 to the power of 2. Okay, so power of 2, that represents the number of bits. Similarly, we can see this. So what happens when we reduce the intensity resolution? Similarly, if we have 256 level, it is having more quality, and if it is having only 2 level, you see only 2 levels. That means 2 colors you are used to represent the image. So one is black color, another one is a white color. So all the intensity values in the image will be clubbed either to white, either to black. But if it are having 256 level means, then you have 8 shades of intensity. So starting from black to white, we have 8 different gray shades also. So by discriminating, we have more levels, it looks good, the quality goods look. So similarly, while seeing this image, you see, so if we are reducing the number of levels, then it seems the image it is a binary image. It has only 2 intensity levels, either black or the white. That is the binary image. Next, we'll move on to the geometric transformation. So, it modifies the spatial relationships between the pixels in an image. The images, what is geometric transformation? It can be shifted, it can be rotated, or the images can be stretched in a variety of ways. We are doing in a mobile phone, no? We are zooming, or we are stretching, we are shrinking. So, how we can use this transformation can be used to create thumbnail views in YouTube and all. We are doing that, no? Create thumbnail views, change digital video resolution, correct distortions caused by the viewing geometry, align multiple images of the same scene. So these are the applications. Why we are interested in geometric transformations. So how it is actually taking place? So here we are actually taking w comma z to be the input space and output space. Two coordinate system you have to take, and you have to project the points from one coordinate to the another coordinate. So if you are transforming from the usually so far we have discussed that we have only two axes, one is the x axis and another the y axis. So if you are plotting the points from x and y axis to w and z axis, then we call this transformation to be forward transformation or forward mapping, and the reverse is called the inverse transformation or inverse mapping. So how we are transforming the points? You see here we have x and y coordinate system, and another coordinate system is w and z. So we are taking the point from the x and y axis. We are taking to plot. You are taking this point and plot it in the x and y axis with the help of a transformation function. So this is your finally x and y axis. So this plotting is known as the transformation, or we can also call this as an interpolation also. So x comma y is actually how we get this x comma y, by applying some transformation function to this wz coordinate system. So we get this. So this transformation function may be w by 2 or z by 2, or it can be anything. Okay, and what is the inverse transformation for this? So there are so many geometric transformation. One is the isometric transformation. So how you get this? So these are having certain properties. You see what it is, this isometric transformation. Iso means same. So same shapes can be shifted. So that is angle, this cos theta, sin theta, everything. So R, capital R, what is this capital R represents? It is an orthogonal matrix. This Euclidean distance will be preserved. It has 3 degrees of freedoms, 2 for translation and 1 for rotation. Similarly, in similarity transformation, so here also we have this transformation matrix. By applying this transformation matrix with this x and y, we get this x dash y dash. So this x dash y dash represents your similarity transformation. So in the similarity transformation, it has certain properties. So that is, it has 4 degrees of freedom, 2 for translation, 1 for rotation and 1 for scaling. Similarly, and the third type is affine transformation. In the affine transformation, we have A11, A12, Tx, Ty, like this we have so many affinity. So, okay, which one is more closer? So, by applying this matrix, we get this x dash, y dash and 1. So, this represents the affine transformation. So, it has certain properties where capital A is the non-singular matrix. Okay, the ratio of the lengths of parallel line segments should be preserved. It has 6 degrees of freedom, 2 for translation, 1 for rotation, 1 for scaling, 1 for scaling direction and 1 for scaling ratio. So last one is projective transformation. It is also known as homography matrix. So here the cross ratio should be preferred. So each one should have certain matrix and it has to be multiplied with our original image coordinates x, y, z. Thereby we get this projective transformation x dash, y dash and z dash. So by applying this geometric transformation, we get the output image, that is G. So how these are the simple steps. For example, how to get this forward transformation W of x comma y? By applying some transformation function to this, we get this T inverse. By applying T inverse, we get this, and from this f of we can get this G. So finally we get this transformed values. Next, lastly, we will see about the image interpolation, that is zooming and shrinking. So interpolation is a basic tool. It is extensively used for zooming, shrinking, rotating and geometric corrections. So here we will see about image shrinking and zooming, that is the resampling methods. So what is interpolation? It is the process of using known data to the estimate values at unknown locations. So it is unknown locations. So before we will see It is projecting the points from one axis, one coordinate system to another coordinate system, that is geometric transformation. But here we are going to estimate the values at the unknown locations. For example, suppose if you take the image size 500 cross 500 and it has to be enlarged to 1.5 times, so that 750 cross 750 pixels. So zooming needs to create an imaginary 750 cross 750 grid with the same pixel spacing as the original, and then shrink it so that it fits exactly over the original image. To perform the intensity level assignment for any point in the overlay, we will see the closest pixel in the original image and then assign that value to the new pixel. After assigning all the intensities to all the points in the overall grid, we expand it to the original specified size to obtain the zoomed image. So this method we call as the nearest neighbor interpolation, because it assigns to each new locations the intensity of its nearest neighbor in the original image. This approach is simple, but it has the tendency to produce undesirable artifacts such as severe distortion of straight edges. It has good side, and it also has its bad sides. For this reason, it is used infrequently in practice. That is, first type of interpolation is nearest neighbor interpolation. I think hope you will be clear about this nearest neighbor interpolation. Next we will see about the bicubic interpolation, which involves 16 nearest neighbors at a point. The intensity value is obtained using this equation, where we have 16 coefficients which are determined by the 16 equations in 16 unknowns. So we get the nearest neighbors of x, 16 neighbors of x comma y. So this interpolation, it does a better job of preserving the fine details than the bilinear interpolation. So this bicubic interpolation is the standard used in commercial image editing programs such as Adobe Photoshop, Corel Photo Paint and all. So by using this interpolation, how the image, that's I shown you just for an example. So first thing, if you see, this is the original image 3692, and next thing are image reduced, next is image shrunk. So okay, first method is nearest neighbor interpolation, and the last two used, next one is bilinear interpolation, and the last one is bicubic interpolation. So it is possible to use more neighbors in interpolation, and there are more complex techniques such as spines, wavelets, than in some instances it can yield better results. So in order to have a good quality by interpolation, that is for zooming, shrinking process, we need to have more number of pixels. Okay, so we should have more number of neighboring pixels so that we can get the better results. So these are the textbooks I have referred for this particular topic. You can also use this. Hope, I think you will be clear with these concepts. So thank you.